Cool. Okay, let's get started with regular expressions. So, a regular expression is just a way of representing a regular language, and it has a few different operators. So, we have. I'll write them to the side actually. Okay, so a regular expression has this. Can anyone tell me what these operators mean? The ones I'm sort of writing up. We could just have terms. Is this? Yeah, this is being recorded. Okay, so a regular expression, it will look something like this. Means nothing, one or more. Oh right, yeah, this, cool. Okay, so yeah, the star means 0 or more occurrences. Okay, and the plus is quite similar, but the plus is where we have to have at least one occurrence. Yeah. And then we have this line. This just means or, so we can either have A or B. It's like this. Okay, question mark means 0 or 1. Brackets is used to define. We use this to define precedence. So if we want to run something before we run something else, say we want to do A, B, or C, D, but we want to do A, and then we want to do this B or C first, and then this D. So these brackets are basically saying let's evaluate this first, and then let's evaluate that A and D with it, the result of that. Okay, and then we have single terms, so we can just have a single term. And so regular expressions are made up of terms and these different operators. To be fair, you might want to. Yeah, that's a good point. You might want to not use this in the exam, but I think Todd said we'd still get marks if we use it. Wait, because there's a few that we covered and there's a few symbols that we haven't covered, but I think we've covered all of these. Let me check. Well, either way, yeah, if you want to do 1 or 0 occurrences, you can use a question mark, but you can also, just as Ollie said, use epsilon or, and then whatever you want to do. So saying epsilon or A is the same as saying A question mark. These two are equal. So if you want to be on the safe side, just stick to that. Cool. Okay, so these are the sort of operators we have in a regular expression. So something like this would mean A followed by any number of B's followed by a C or an epsilon. So we can rewrite this as epsilon or C. So this would be something like A, B, B, B. Would this string or would this word be accepted? I'm going to write a few words. Yeah, I think we were. Okay. Yeah, I think we can use a question mark, to be fair. This is the first handout. I'm just looking for... Yeah, no. The only question marks I see here are part of the questions. Where, Kevin? Top of second page. Oh, right. Yeah, so this is what defines plus and question mark. So I guess we can use it, and yeah, more operators that you can use. So we're good on that front. Okay. So out of these words, let's just quickly go over what words would be accepted by this regular expression and what would be rejected. Okay, so this first word is 2 A's, and then 3 B's, and then an A. As soon as we read in the second A, we've not got anything to sort of take in that second A. We only expect 1 A before everything else. So this would be rejected. Again, this has multiple A's, so rejected. This next one, we take in an A, and then we're taking in 0 or more occurrences of B. That's fine. That takes these 3 B's. And then we have an epsilon or C. In this case, this is just the same as this with an epsilon. So this would be accepted. And ABC, we take in an A, we take in 1 occurrence of a B, and then we take in this C from this OR here. So this would also be accepted. I hope that makes sense to everyone. Okay. So regular expressions, we can use it to represent a language. A language is just a set of words that are accepted by that expression. Okay. In terms of the different operators, they have an order of precedence. So at the very top we have this asterisk symbol, and then we have juxtaposition, and then we have OR. So at the very top, something like A star, this star has the highest precedence. So if we have A star B, or let's say we have A B star, this star only applies to this B. It doesn't apply to this whole term. If we wanted to apply it to AB, we'd put brackets around here. Juxtaposition is when we just concatenate two things, like A, B, C, D, or concatenate multiple things. This is juxtaposition. You can imagine it as just concatenation. And then this is OR, so we have something like A or B. Because juxtaposition's higher than OR, if we have A or B, C, this is not the same as A or B and then C. This is saying either A or B, C. If we had something like a star here, this would be either A or B followed by any number of C's. One of these two options. So how I like to sort of imagine it is the higher up this order of precedence we go, the stickier it is to the character or to whatever it's next to. And again, we have brackets. Brackets can just contain anything, really. Just like in maths, we can then apply operators to all of the stuff in the brackets. It collects it all together. Okay. So, every regular expression represents a regular language. Any language L in sigma star can be represented with a regular expression if it's a regular language. So, sigma is just our alphabet of characters. Let's say it's just A, B. Okay, so one example alphabet, let's call it L, equals AA, BAA, I don't know, okay, let's say AAA. So we might have an alphabet where it's just A's. Any string that contains only A's is accepted by this language. And L is a subset of sigma. Sigma star, sorry. Okay, so this is an example of a regular language because we can describe it as a deterministic finite automaton. So for a language to be representable as a regular expression, that means we can also represent it as a DFA. And we can imagine something like this. If we had an initial state, we want to accept anything with 1 or more A's. So this is the same as A plus, or A and then A star. This is the language that L is representing. So AA star, let's think about it. We have an A. We have to take in at least one A, and then we can take in any number of A's after that. And we accept here. So if we take in something else, if we take in a B, because that's our only other character in our alphabet, we can just go to reject state. No matter what we take in after that, because we've seen a B, we are not going to accept that string. In the same way, if we take in a B from here, so after the A, if we take in a B, we instantly reject that as well, because we don't want to take in any strings that has something like AAAAB, because that's going to send us to this error state. And then this DFA just represents the what this regular language represents. If we can represent a language as a DFA, we can also represent it as a regular expression, and vice versa. And so we can use this to have a robust definition of what a regular language is. Oh no, okay, one second. Okay, cool. Witty, the list of things we're covering is in upcoming today. I'm just doing regular expressions and regular languages quickly. Okay. So. Okay, so when we represent a reject, so L can be represented by a regular expression. If L can be represented by a regular expression, then what that means is we can also represent that as a DFA. And the reason why that's true is because of Kleen's theorem. So, by Kleen's theorem, L can be represented as a DFA. And so we can convert regexes to DFAs and vice versa. And we can use this to do all sorts of things. Things we can do with DFAs that we can't do with regular expressions, like checking if two different regexes are equal. We can't easily do that with just two regular expressions, but if we convert them both to DFAs, we've seen in a previous session how we can check if two DFAs are equivalent by tracing through both of them simultaneously and making sure the states are both accepting or both rejecting. So we can compare regular expressions in that same way by converting them down into DFAs and then comparing the states. We've got a few interesting questions here. So, is the matching problem for the regular expression C, BB, or CA star decidable? In other words, is there some program that when given a word W over our alphabet sigma, returns true if W matches this, and false if it doesn't? Doesn't really help that we have the answers. I'm going to cross them out so we can kind of discuss through them. Okay, so... Okay, the answer to this one's yes. I think we've all seen that. So the idea is this is a regular expression. If we can make a DFA which represents it, this DFA represents an algorithm because it's a finite set of states and an algorithm is just a finite set of instructions. And so this matching problem would be decidable. Is the matching problem for this regular expression decidable? It's a regular expression, so therefore it's representing a regular language. And by Kleen's theorem, we can represent it as a DFA, which is essentially synonymous to an algorithm. So this is also decidable. Is it the case that for every regular expression E, the matching problem is decidable? So no matter what this regular expression is, it will always be decidable because we'll be able to have some DFA which represents how we can decide whether it's in the language or not. Is the matching problem for regular expressions decidable? In other words, is there some program that when given a regular expression E and a word W, returns true if W matches E and false if it doesn't? What do we think about this one? Question 4. Okay, yeah, so we can essentially just represent it as a DFA. We can imagine that we have some program which, because a regular expression is made up of a finite set of symbols and a finite set of operators, we can create a program which simulates running it. And so we've seen this with websites like regex101.com, which just we type in a regular expression and it sees if we can match it with a word or not. Okay. Yeah, cool. And finally, is language equality for regular expressions decidable? So is there some program where if we give it two regular expressions, E and F, it tells us if they represent the same language, it says true if they represent the same language and false otherwise. And whatever we think our answer is, let's try and justify it. No. Okay, what makes us say no? Depends on the... Okay, I mean, the answer that we've got is yes, because even if it depends on the alphabet's always going to be finite. So when we're it's not about just trying two different words though. It's we can use that theory of converting the regular expression to a DFA and then tracing through the DFAs to see if they're equal. Because we know we have a systematic way of checking if two DFAs are equal. And we also have a systematic way of converting a regular expression to a DFA. So we have a way of putting both of those together to check if two regular expressions are equal. Okay. I think this is probably the last part I'll cover in terms of regular expressions. So in the previous section we asked whether certain problems can be solved at all. Another question is, can they be solved efficiently? So we want to be able to make some sort of efficient solution. We don't want a horrible... Yeah, I'm just trying to think how this would be in terms of regular expressions. I mean, in terms of the DFA side of things, we want to make a minimal DFA because then it will take the least number of steps for any given input. And I guess when you convert that back to a regular expression, it's a minimal regular expression. But yeah, the idea is the main thing we want to keep in mind is we can convert between regular expressions and DFAs, and both of these represent a regular language. So we can have irregular languages, which can't be represented by a DFA. Can anyone give me an example of an irregular language? A to the n, b to the n. Okay, yeah, so if we had something like a to the n, b to the n, such that n is greater than or equal to 0, if this was our language L, L is irregular. Reason being, we can't represent this as a DFA. So this wouldn't be a finite automaton. We'd need an infinite number of states to represent this. I won't go into too much detail there, because that is... We covered that yesterday. There's a good old irregular checker. Check out Ashpreet's video on that. But, yeah, so these are examples of irregular languages. Because we can't represent it as a DFA, it's not a regular language. And that's how you'd sort of go about proving that. But if we want to prove something is a regular language, all we have to do is show that we can represent it as a DFA. Therefore, it's regular. By Kleen's theorem, we can represent it by a regular expression, and it's a regular language.